Welcome back to part 2 of magnetic fields. In this video we're going to look at the current carrying conductors producing magnetic fields and how we utilize that concept in a solenoid, and we're going to look at this concept of the magnetic field strength from a current carrying conducting wire being given by this equation where B equals mu naught I over 2 pi r. So the key learning outcome for today is to solve problems involving the use of B equals mu naught I over 2 pi r and understand what each of these terms actually means. A solenoid is a continuous wire wound around a cylindrical core, usually something non-conductive like plastic. It can be considered a series of loops stacked together, and last lesson we looked at a single loop and we said that the magnetic field is always sort of going through it in a direction depending on the direction of the current. This means that if we create this tube, this solenoid of looped wires, you're going to have that continual magnetic field from one side to the other, which virtually creates almost like a magnetic launching tube where you've got this magnetic force coming in this side, traveling through the tube all the way to the other side. To find the direction of the solenoid and the field, we use the right-hand rule. So similar to what we saw before, the right-hand solenoid rule, grasp the solenoid with your right hand, your fingers are in the direction of the current, and your thumb now gives you the direction of the north pole of the solenoid and the direction of the magnetic field outside. So it's almost the inverse of what we saw before. Previously we said use your thumb, wrap your fingers around the loop. Now we're saying wrap your fingers around the loops in the direction the current is spiraling, and your thumb now points in the direction of magnetic north. If you forget this, you can ultimately still do the same thing using just a single loop. So if you forget how to orientate whether I grasp through a single loop or the whole set of loops, just consider one loop and go, alright, my thumb now points in the current direction, which if we zoom in as we see here is up. My fingers curl through the loop, which means the magnetic field is pushing towards the right-hand side, or sorry, the left-hand side. Therefore, if I translate over here, you'll notice it works out exactly the same. The magnetic field is pushing towards the north side. If I use the solenoid rule, my thumb now points towards the left-hand side, so I get the same answer. In terms of the strength of a solenoid, there are three key things that can affect the strength of a solenoid. One is the number of coils. So by increasing coils, creating more and more closer together, we create a much more strong magnetic field. Increasing the current that passes through the coils, because a greater current will induce a greater magnetic field. And thirdly, placing an iron core inside the solenoid also increases the magnetic field strength generated. A solenoid with a current flowing through it is often referred to as an electromagnet. Whilst the power is on, current is flowing through the circuit and we're producing that magnetic field. As soon as we turn off the power, that current stops flowing and therefore the magnetic field vanishes. This can be used for a whole range of applications. One of the common ones that we might see is things like wrecking yards that are moving scrap metal, because we can just switch on and off the magnets so we can pick things up, hover over where we want, switch it off, and it'll just drop everything. Solenoids are often used as electrical switches to control water, air, or hydraulic flow as well in a whole range of machinery. And you can see a couple of different image examples. So this might be like a gas pipe, for example. You have an electronic solenoid that will open and close a valve here. So when the magnetic field is generated, it might pull this little needle up and it'll let flow through, whether that's water, air, gas, etc. When that switch is closed, the magnetic field drops, the spring pushes it back closed. So it'll always close if power cuts out. Lots of different applications for this. You often even see solenoids in things like magnetic locks. So often fire escapes and things use electromagnetic locks. The ones at school use the same concept, so that if for whatever reason the power is cut, those locks will disengage and you can always open the door in a power outage. Another example of a solenoid can be seen in this simple circuit below. So this is a circuit for an electric bell. What I want you to do is take a minute and try and identify what's going on in the circuit and how does this bell ring continuously when the switch is pressed, or aka the circuit is closed. So take a moment, see if you can explain the answer. Okay, let's have a look at how this is working. So if we push the switch, it completes the circuit and the current flows, so that part's not too bad. The electromagnet creates a magnetic field which attracts the soft iron armature here. So it's going to pull it towards the bell, which means as it pulls it in, it's going to hit the bell. The spring then moves to the left, and that circuit is then broken. Once the circuit is broken, the magnet switches off, and this returns back to its original position because of the spring tension. It's going to re-engage the circuit, which then creates the magnetic field, pulls the armature again back towards the electromagnets, which hits the gong. And it's going to repeat at very high speed, so it's constantly switching on and off that solenoid, which creates your ringing bell effect. The magnetic field strength, which remember from last lesson is capital B, is directly proportional to the current flowing through the conductor. So we can say that B directly proportional to I in this case. The magnetic field strength is also inversely proportional to the radial distance from the conductor. So the magnetic field strength is directly proportional to 1 over R, very similar to what we saw with electric circuits previously. Therefore, the magnitude of the magnetic field strength near a current carrying conductor is given by the equation B, magnetic field strength, equals mu naught times current divided by 2 pi r. Remember, 2 pi r is circumference, so this is the radial distance. Remember that r is the radial distance in meters, B is magnetic field strength, so our units are Tesla. Mu naught over 2 pi is really just a constant. And this is the constant for a magnetic field around a conductor. Given on the formula sheet, it's equal to 2 times 10 to the negative 7 Tesla meters per amp. So that is really just a current. So we could replace this with just a letter, just like in Coulomb's law, for example. We said that the 1 over 4 pi epsilon naught we can just call K. In this case, mu naught over 2 pi is also just a constant, so we could replace that with whatever we wanted. But we just need to know that it is 2 times 10 to the negative 7 Tesla meters per amp. So a couple of questions for you to practice. We've got a straight current carrying conductor here, 2.3 amps. Calculate and state the direction of the magnetic field at P if it's 12 centimeters below the conductor. Calculate the magnetic field at the point of P. Use proportionality to describe. So remember, we're talking about using proportionality. Here we've got state, so this is words. Here we've got calculate, proportionality, calculate again. So have a go at these questions. Answers will be up in 1 minute. Alright, so for A, it is into the page. We can use our right hand rule again. We can see that our thumb would point in the direction of the current, our fingers would curl out. So at the top side of it, it would be coming out of the page here. So we would expect our little dots. It's curling around the wire and then going back into the wire, or sorry, into the page at point P. Calculating the magnitude of the magnetic field, we use our mu naught I over 2 pi r. I is 2.3 amps. This is my 2 times 10 to the negative 7. And here I've got my 0.12, which is centimeters in meters. So I get 3.8 times 10 to the negative 6 Tesla. Using proportionality, we want to see something like, because the magnetic field strength is directly proportional to I, therefore at P, it'll be 3 times larger if the current is increased by 3. So tripling this triples magnetic field strength. If we have this magnetic field strength 5 centimeters from the conductor, calculate the current. So all we're doing is we're using the same equation, but we're rearranging for I, which is our current. So we know the magnetic field strength, therefore I equals this, the magnetic field strength, times the radius divided by our 2 times 10 to the negative 7. Plug in all of our values and we get 13.6 amps of current flowing through this circuit. Next one is to calculate the magnetic field midway between the 2 straight current carrying conductors shown below. So pause the video now, have a go at this one. I'll put the answer up in just a minute. Okay, let's look at the answer. So, the magnitude of the field is, we're talking due to conductor 1 first, is 1 times 10 to the negative 5 Tesla out of the page. Now we go, what is the magnitude of the field due to conductor 2? And that's 1.6 times 10 to the negative 5 Tesla out of the page as well. Given that magnetic field is a vector, the total magnetic field midway between the two is the vector sum of the magnetic fields, just like the superposition we saw with electric fields. So if we had the 1 times 10 to the negative 5 out of the page, plus the 1.6 times 10 to the negative 5 out of the page from the other conductor, the total effect of that is to have a magnetic field strength at that point of 2.6 times 10 to the negative 5 out of the page. Another way to think of this is, remember we said in the previous video that the number of magnetic field lines denotes the strength of the field. This is telling us that at this point in between, we've got field lines both going in the same direction, which is important because then they're not kind of cancelling each other out. But you're going to have some field lines from conductor 1, and then you're going to have some from conductor 2, which means the total effect is to have more field lines in between the two conductors, and more field lines signifies a stronger field. So we'd expect the answer to be greater than the individuals there. A really commonly known application of this sort of concept of solenoids and magnetic fields is the railgun.
This is the US military's most powerful cannon, the Electromagnetic Railgun, which can shoot up to 100 nautical miles at Mach 7.5 and impacting the target at Mach 5, using only energy as its propellant. The high-velocity projectile will destroy land, sea and air targets purely from its kinetic energy, rather than with conventional explosive warheads. So what is a railgun? Well, the EM Railgun launcher is a long-range weapon that fires projectiles using electricity instead of chemical propellants like gunpowder. Magnetic fields created by high electrical currents accelerate a sliding metal conductor or armature between two rails to launch projectiles at 4,500 miles per hour. Basically, it shoots a big solid metal projectile at very high speeds at vast distances and does damage using kinetic energy, only using electricity to shoot. The railgun works by storing power for several seconds, generated from an external source, like a ship. After the weapon is charged with some 32 megajoules of energy, its capacitors send an electrical pulse down two long rails, one negatively charged and one positively charged, generating an electromagnetic field that fires the projectile along the two rails at up to Mach 7. Using extreme speed, the warhead impacts with high kinetic energy, ripping a hole through whatever it was aimed at. The 25-pound projectile is a non-explosive bullet, like a big dart, inside an aluminium alloy casing or sabot, that falls away after the projectile leaves the barrel. The greatest advantage of an EM railgun on a naval vessel over traditional explosive round weapons is the safety aspect, as no propellant is required to fire the projectile, and no explosive rounds are stored in the ship's magazine. Railguns have been around a long time in sci-fi TV shows and movies. The most recent I can think of is from the TV show The Expanse, where all the big military spaceships all use railguns, and in the 2009 movie Transformers 2, a naval vessel uses a railgun to shoot a transformer off the pyramid. But the EM railgun has two major complications. The weapon takes an enormous amount of power to fire, and it literally tears itself apart with use. The railgun has already been in development and testing for over a decade, with total cost exceeding $500 million. In its current form, the railgun simply requires too much power for widespread use. The problem is, the only ships that will be able to generate the gargantuan 25 megawatts of power required to fire the railgun are the Zumwalt-class destroyers, which will use Rolls-Royce turbine generators to produce as much as 78 megawatts of power for the ship. But only 3 of these technologically advanced warships will be produced. A bigger problem is that the railgun will shred its internal components to bits if it is fired enough. You can see parts of the rails themselves erupting from the weapon as plasma when it is fired. The projectile is leaving at incredibly high velocities, and it accelerates down the barrel. The contact between the sabot and the rails simply erodes the gun itself. The other short-term solution is to develop a railgun that uses less power. An EM railgun that could fire a projectile at 2500 miles per hour instead of 4600 miles per hour and hit a target at 50 nautical miles instead of 100 nautical miles would still be incredibly useful, especially if the Navy could mount the weapon on existing warships. A less powerful railgun still has all the advantages of being cheaper to fire and removing dangerous explosives from a ship. Anyway, that's the end of this video. Thanks for watching, and we'll see you next time. Bye bye.
From here, have a look at the workbook questions in the SASTA book. For this section, we're looking at question 158 to 166, and I'll see you next lesson.